Ayush, and my registration number is ui2620. And today we're going to discuss about the halting problem, which I've chosen as a topic for the optional assignment. So to discuss about the halting problem, we need to discuss, we need to know uh, about certain topics, and that is decidable language, undecidable language, and we need to know what Turing machine is. So a decidable language is like we can take an example. A decision problem P is said to be decidable uh, if the language L of all yes instance to P is decidable. Example, acceptance problem for DFA. Then for undecidable language, a decision problem P is said to be decidable if language L of all yes instance to P is not decidable, or language is undecidable. If it is not decidable language may be partially decidable language or something else, but not decidable. Then a Turing machine is a mathematical model of computation. A Turing machine is a general example of a CPU that controls all data manipulation done by a computer. Turing machine can be halting as well as non-halting, and it depends on the algorithm and input associated with the algorithm. So now we're going to move to the main topic, the halting problem. So a halting problem is something we can have an example for it. So for example, there's a problem and an algorithm and in which we put an input, and the algorithm is not able to get out of the loop, and the input that we have given force the algorithm to be in the loop. We cannot decide uh, before putting the input into the algorithm to whether we it will go into the loop, the endless loop or not. So a halting means that the program on a certain input will accept it and halt, or reject it and halt, and it will never go into an infinite loop. Basically, halting means terminating. So, so the question that arises is, can we have an algorithm that tells us whether the problem will halt or not? So basically, what it says is whether we can design an algorithm that tells us the that the input that we have given into the algorithm will go into an infinite loop, or will it stop or not. So in terms of Turing machine, will it terminate when run on some machine with some particular given input string? This is an undecidable problem because we cannot have an algorithm which will tell us whether a given program will halt or not in a generalized way. By having specific algorithm in general, we can't always know whether it'll go into an infinite loop or not. The best possible way is to run a program and see whether it halts or not. This way, for many programs, we can see that it will sometimes go into loop and always halt. So we can prove that halting problem is unsolvable, or we can basically we can prove that we cannot uh, find a way to uh, to decide whether a program will go into infinite loop, or whether it will halt or not uh, just before running the machine. So we can prove this by contradiction. So we are taking here an example. So our problem statement is, can we design a machine which, if given a program, can find out program will always halt or not with a particular input. So over here, we'll start. So here we are assuming that we can design that kind of machine, a halting machine. So we're gonna name it HM, and then we'll put an argument as P and I, where HM is the machine program, P is the program, and I is the input that we're gonna put into the machine. On taking the input, the both arguments, the machine HM will take the program P, either halt or no, it's gonna halt or not. We're gonna see that. If we can design such a program, this allows us to write another program. We can call this program CMX, where X is any program taken as argument, and according to definition of the program CMX, we can like see how the algorithm will work using this diagram. So HM will take is having P, the program, and I as an argument. So it'll either halt or it may not halt. And this is the subprogram, the CM, like the CM machine. It is having the program X, and it will check if X halts or it will loop forever. So in program CMX, we can call the function HMX, which we have already defined. And to HM's function, we pass the argument X, the algorithm X. According to the definition of halting machine, it can take two arguments. One is the program, and another one is the input. Now, in the second program, we pass X as in program, X as input as well for the function of the halting machine. We know that the halting machine gives two outputs, either halt or not halt. But in the case second program, when uh, halting machine is taking X as an input, X and X is the algorithm in it, well, halt loop body tells to go in a loop and then it doesn't halt. That means the loop it's asked to return. So it'll go into an infinite loop. Now we can see it over here. Like it'll go to an infinite loop as it'll not halt. Now we can take one more situation where the program CM is passed to CM function as an argument. There would be some possibilities condition as if which is not possible. So over here we can see when we pass we put it into recursion, we see it means it'll go to like forever loop or it'll halt. So in this case it will never halt because of the above non-halting condition over here. So it is impossible for outer function, that is the halting machine function, uh, if it is in the loop, and also it is impossible for outer non-halting function to halt even after in the inner code is halting. So both conditions are not halting for CM machine, even though we had assumed in the beginning that it would halt. So this is the contradiction, and we can say that the assumption was wrong, and this problem, the halting problem, is undecidable. This is how we prove that the halting problem is undecidable, and uh, this is how we get to know that uh, this is the issues with the Turing machine, and we get to know that we cannot decide before putting an input into a machine how it will react. So we have to put an input, and then only we'll get to see how the algorithm reacts to the input. So that was the halting problem. I hope you understood it and it was well. So thank you.